let's go. Let's just get into it. So this is undergraduate science laboratory, and like we actually had to do like real science experiments in this thing. But yeah, right now what we want to do is just pretty much memorize all of these procedures. So let's just get into it. First thing that we want to do is experiment 1, which is the calibration of volumetric glassware. So this was something which we didn't actually ever use again because we had new glassware every single time, but let's just get into it. So in this laboratory experiment, there are 3 types of glassware typically used by analyst chemists. They are a volumetric flask, a volumetric pipette, and a measuring cylinder. So yeah, just gonna put a list. Okay, this was the wrong one. Sorry. So the so the types of glassware, 3 types of glassware by what? By some sort of chemist. It is analytical chemist. These are, so first is a volumetric flask. So volumetric, I know. I type very slow and this is going to take some time, but whatever, just bear with me. Volumetric flask. The flask reminds me of the application flask. Anyway, volumetric pipettes or pipettes or whatever this thing is. I think it's this. I think the spelling is wrong. It should be P and P. Nope. Spelling is just wrong, isn't it? I think it's like double T or something. Pipettes. Yeah, we don't know. Anyway, so volumetric pipettes, then a measuring cylinder, right. So these are the 3 types of glassware. These tools are used essentially when performing gravitational, so gravimetric and trigonometric analysis. So usage of glassware. So it's used in what? One is the gravimetric and trigonometric analysis. So analysis and trigonometric analysis. So these are the 2 ways that you can use these. Then to avoid introducing systematic errors in measurements, each of these instruments must be properly calibrated, right? Calibration is done. So why do we do it? To avoid systematic errors. So what is a system over here? This is mainly just the temperature and chemistry related things. So the reaction conditions, that's what we are talking about. Like whatever the system temperature is, or some other things are like humidity, whatever. Depending on that, your glassware like changes its size, right? Yeah. Okay. And to reduce the random errors inherent when using these instruments, their property must be thoroughly understood. Okay. Fine. So this I didn't get. When using these experiments, the proper use must be thoroughly understood. Sure. So it's just to understand like how do you use this thing. That's not a big deal. The quality of the measurements obtained from these tools depends heavily on the care taken in calibrating and in using each instrument. Okay, fine. It's random bullshit. So the pipette is so it's PIP-T. Yes. So it's E over there. Just a second. रिकॉर्ड कर रहा हूँ right, sorry, just was interrupted by something else. Anyway, so the calibration reason, we got that. Then the quality of the measurements obtained from these tools depend heavily on the care taken in calibrating and in using each instrument. So let's get to it. Tips for the correct use of the volumetric glassware. So how to use the volumetric glassware? Sure. Oh, glassware pipettes. So how to use VPs? The pipette is used to transfer a volume of solution from one container to another container. Most volumetric pipettes are calibrated. So how to use YVP are used, right? The volumetric pipettes. So one is, in fact, that's the only solution. So to transfer a volume of solution from one container to other, to transfer solution from one container. So this is very kind of obvious, to the other. So yeah, volumetric pipettes are in fact glassware, and they are different from normal pipettes that you have. Yes, right. Okay, so the most volumetric pipettes are calibrated to deliver with certain amount of the liquid remaining in the tip and as film along the inner barrel after the delivery of the liquid. They're calibrated to deliver. What does that even mean? With a certain amount of liquid remaining in the tip and as a film along the inner barrel after the delivery of the liquid. This is some weird thing going on. And the inner, okay. Oh, okay, I get it. So it's like whatever amount of liquid actually went away, that is whatever was uh, written by the marking, right? So this liquid that is inside of it plus whatever went outside, that's the total amount of liquid, but we are only going to measure by the pipette the amount that went outside, which makes sense perfectly, right? So they are calibrated to deliver. So VPs are calibrated so that the amount of liquid, outgoing liquid is probably more like it, okay, that is leaved, that leaves the pipette is given accurately by the reading. Right. Yeah, and not, so this is disregarding or discounting the liquid that stays inside the pipette. So that is that's given accurately by the reading. Sure, okay, got it. So that's 2D level calibration. Then what else do you have? Right, so the liquid in the tip should not be blown out, which makes sense. So to fill the pipette, insert it vertically in the liquid with its tip. So how to use it? How to use VP? So first insert vertically in liquid with the tip near the bottom of the container, right? Tip near container's bottom, right? Apply suction to draw the liquid above the graduation mark, okay. Suck a little more, and then suck a little more than the graduation mark. Sure. Then quickly place a forefinger over the end of this stem. Withdraw the pipette from the liquid and use a dry paper to wipe off the stem. Okay, place a forefinger or place a finger or whatever over the end of the stem. So the stem is just like the tube itself, right? So it will have like an open end. So let's just put something over there so that the air doesn't leave. So withdraw the pipette, or there it doesn't enter is more like it. Withdraw the pipette from the liquid and use a dry paper to wipe off the stem. Sure. Okay. Pull out. This is really sus sort of. Never mind. Pull out and clean up. Yes, I know what you're thinking. I'm thinking the same thing, but whatever. Okay. So basically, you insert, you do a little more than what's necessary, you place a finger, and then you pull out again. This is very similar to something. Never mind, never mind. This is just bizarre, but yeah. Okay, so use a dry paper to wipe off the stem. Or more like clean up the pipette from outside, because from inside you can't. It doesn't make sense because you absorb the stuff that is inside. Okay, withdraw the pipette from the liquid and use a dry paper to clean. Okay, cool. Now place the tip of the pipette against the container from which the liquid has been withdrawn. Against the container from which the liquid has been withdrawn, and drain the excess liquid such that the meniscus is at the graduation mark. Drain the excess liquid. Oh, okay. Against the container. This is fine. Just inside the container is more like it. So we shouldn't say inside, more like just hovering above it. Drain the excess liquid such that the meniscus is at the graduation mark. Move it to the receiving container and allow the liquid to flow out. Avoid splashing. Of the pipette freely. When most of the liquid has drained from the pipette, touch the tip of the wall to the wall of the container until the flow stops for an additional count of 10. Okay, cool, got it. So release again. But freely, or never mind. Release again into the container. Like without insertion, right? Till the graduation mark is okay, till the level reaches the graduation mark. Okay, cool. Then after that, so liquid has drained from the pipette. Touch the tip of the wall. Okay, touch tip to wall of container and hold for 10 counts so that leakage flows. I shouldn't even call it leakage. All liquid in the tip is cleared. Cool. This is very similar to something else, but yeah, we shouldn't really think about that. Right. So liquid has drained from the pipette. Touch the tip of the wall to the container until the flow stops. Oh, okay. And hold, okay, till the flow stops. Plus for 10 more counts. Sure, that's fine. Okay, so that's just volumetric pipettes. Now volumetric flask. So the volumetric flask is used to prepare standard solutions. So why volumetric flask? Used to prepare standard solutions or in diluting a sample. So preparing standard solutions or in diluting a sample. Fine. Most of these flasks are calibrated to contain, right? This is a calibrated to contain. Okay, that's just calibrated to contain. This was like the, yeah, so to deliver, that is 2D, so TD calibration, this is to contain. Cool. Yeah, to contain a given volume of the liquid. Fine. So when using the flask, the solution or solid to be diluted is added and wait, what? The solvent is added until the flask is about 2/3 full. What the why? It is important to rinse down any solid or liquid that has adhered to the neck. So okay, never mind. This is I'm just gonna write it in here. Sure. So I'm just gonna write down how to use. So first, what we do is, when using a flask, a solution or solid to be diluted is added. Okay. Add the solution or solute to be diluted. Add solvent till 2/3 flask is full. You sure about it? The flask is about 2/3 full. It is important to rinse down any solid or liquid that has adhered to the neck. Okay, so rinse down anything stuck to the neck. Okay, that's cool. Swirl the solution until it is thoroughly mixed. Swirl till mixed. Fine. Now add solvent until the meniscus is at the calibration mark. So add more solvent. Or okay, let's just call it add solvent till level at, wait, what? Okay, till meniscus. The meniscus is just like you know, it's basically like the base of the actual meniscus, right? Yeah. Calibration mark. At calibration mark. Okay, cool. That's amazing. If any droplets of the solvent adhere to the neck, use a piece of tissue to blot these out. Droplets of solvent adhere to the neck. Okay. Use a piece of tissue. Wait, so it's the same. Yeah. So it's, oh, so before it was like rinse down. Wait, what the hell? Oh, okay. To the inside of the neck. Clean the outside of neck. Okay, so this time you're actually doing it like both. Okay, with tissue. Cool. So it's not just called clean, it's actually called blot, since you're probably going to be using blot paper or whatever. So stopper the flask securely and invert the flask at least 10 times. Interesting. Invert. Okay. Tighten the stopper, or I just call it stopper. So stopper the flask, and I'm gonna write it in italics because this is a very weird word, although I get what it means, but still unusual. right? And so invert 10 times for mixing. Okay, that's amazing. Cool, that's amazing. Next, so a general calibration procedure. General procedure. So first thing that you do is volumetric glassware is calibrated by measuring the mass of the water that is contained in or delivered by the device. This mass data is then converted. Okay, mass of water. It's kind of also like the volume, isn't it? Anyway, this mass data is then converted to the volume data using the tabulated density of water at the temperature. Oh, okay, I see. Oh, okay. So the marking that you will have on the glassware will actually be like how much of mass there is. That's a very weird scenario, isn't it? Sure is. So now this mass data is then converted to volume data. Okay. Calibrated using mass values at levels after measurement you have to convert it back. Okay, so first it's done that. Mass is converted to volume. For the temperature of the experiment. Okay, whatever. Using density of water. Right. So what that suggests is that you'll always probably have to put water in there, right? Wait, no. You in the end just care about the volume, so it doesn't matter what you put in. It's the same volume, right? Yeah. So mass is converted to volume, and then that is what is you actually like. You're gonna mark that instead. Okay, cool. Data converted to standard temperature 20 degrees Celsius. So conversion from room temperature. Okay, that's probably not a good term. From temperature of experiment to 20 degrees Celsius or room temperature. That happens. Okay, then so in this experiment a volumetric flask, a measuring pipette and a volumetric pipette will be used to will be using gravimetrically determined water. In each case the measured mass of the calibrate. Okay, so once again just that they are giving us instructions. In each case the measured mass of the calibrating water will be standardized to 20 degrees Celsius at room temperature. The density of the water at different temperatures. I don't think we'll have to memorize this at all. So but yeah, at different temperatures you have different densities, so it's kind of a rule that at higher temperatures your water will be like higher volume, right? So in that case your density will be lower. So like at 30 it's 0.995 something, here it's 0.999 whatever. So at 0 degrees Celsius it will be like exactly 1 because that's just the way it's defined, I think. But yeah, so take 3 different volumes of water. So instructions: take 3 different volumes water from a pipette, flask and measuring cylinder and measure the weight of the liquid for each container and measure their weight. Okay. And calculated, more like, yeah, whatever, and measured volume. Okay, cool. So this is done by a weighing machine, and this one is done by the markings that we have on the flask. So take 3 different volumes, you do that, then note the difference between the actual weight and the calculated one. Right. Find difference in calculated weight and measurable. And estimate up to 3 decimal places. Right. So estimate up to 3 decimal places. And yes, this is actually going to give you like the kind of error that you would expect, because so this is the absolute error that you would expect, right? If you just subtract it, yeah, that's kind of what is going to happen. And that's why we're doing it like 3 times, so that you can do sort of a mean or something like that, right? So all the results should be given in tabulated form, whatever, we don't care. So that's this one. It's, I think, very easy. Yeah, that's calibration. Let's close that. Let's go to electrolysis. So this one just has 2. Oh, interesting. Oh, this one is actually pretty short, isn't it? Short. This is electrolysis. This is, I think, an experiment which we did later on, right? So it's still fresh in the memory. So, okay, if I remember correctly, all you had to do was just take 3 kind of water. So you have distilled tap water and water with salts added in. So you'll do electrolysis for each of these. For distilled water, you obviously won't see anything. For tap water, you will see bubbles, but you won't actually get enough hydrogen gas so that you actually can measure how much of hydrogen gas there is. So measuring hydrogen gas pretty much tells you how much of the reaction has progressed. So you have to just give readings of hydrogen gas so that we can do something. And finally, you also have the NaCl and MgCl2 thing. So it just so happens that for NaCl you will actually have like less amount of H2 generated. Okay. So once again, electrolysis is a process in which a chemical reaction is carried out using a just a second. Right, as I was saying, actually kind of forgot what I was saying. Electrolysis. So, okay, actually this is probably, never mind. It's a process by which a chemical reaction is carried out using electric current. In water electrolysis, water is oxidized at the anode to produce oxygen and reduced at the cathode to produce hydrogen. Sure, this is like kind of obvious. We can remember that. Hydrogen is used to power fuel cells, fuel cell cars, and trucks. So H2 is used for that. So H2 is used to power or to fuel what? Okay, I'm just gonna copy the same thing. To power fuel cell, cars, and trucks. So basically, it's like a clean sort of a thing, which I mean it is actually not, since you require electricity, which in turn requires coal to be burned. So it's all like thermodynamically very inefficient since you have so much of transfer happening. But yeah, you can kind of pretend that it is a clean source at the end, in the end, right? So yeah, so this is one of the cheapest, and it's not cleanest, but fine. The cheapest and cleanest way Right. So to produce hydrogen gas, it is certainly the cleanest way. Because the other way to do it is using HCl, which not good. HCl or H2SO4 or whatever acid you want. Just take a strong acid, just put it on some metal, and hope that you get lots and lots of H2, and you will obviously. But that's not a very nice thing to do. That's bad, actually. But yeah, so it's the cleanest way. So electrolysis, or I'm just gonna say cleanest and cheapest way to produce hydrogen. Right, it's supposed to be cheapest. Okay, then the efficiency of water electrolysis highly depends on the electrodes and the electrolytes used in the process. Okay, so efficiency highly depends on the electrodes and what? And electrolytes. I mean, there aren't really any other parameters which you can change, so okay. But yeah, I suppose yes, you are correct. It does depend on it. My God, that's such a surprise. Okay, so the materials that you require. First is a copper wire. Next you have graphite rods. So these are our electrodes. Why graphite? I hear you say because it's more or less inert. It's pretty hard to, to kind of like transfer, like to make some new chemical compound involving carbon when you have electrolysis going on. Yeah, it doesn't usually work like that. I think I kind of remember something about it. It's like one of the reactions is much faster than the other one or something like that. So like carbon being like it mixing with the water. I shouldn't even say mixing, reacting with the water thing. That happens at a much slower rate than the reaction of H2 molecules. So sorry, H2 atoms and all that stuff. So okay, it's more or less inert. A graduated burette. Graduated. You get the thing. It's gonna have markings everywhere. Right, it's like a tattooed burette. So marked with markings. Yes, I type really bad. Marks, whatever that thing is. Burette A. How do you even write this thing? Burette. I need to write in French pretty much. A battery. So it's a 9-volt PP3 battery. I don't know what PP3 means, but yeah. And a beaker. I mean, kind of obvious. Where else will you keep your water? And obviously electrolytes. I need some electrolytes, in fact. I haven't had food for who knows how long. Actually, I just had a donut, but you know, the usual. So, the procedure. These are just materials. Steps. First, connect the electrodes to the power source. Okay, that's pretty straightforward. Connect electrodes. That's kind of a dangerous first step, but okay, you wanna go with that. Then you place the electrodes in deionized water-filled inverted burette. Usually it's supposed to be the opposite. This is very weird. Okay. Place electrodes in deionized water-filled inverted burette. So place electrodes in DI water. Sure. Apply voltage to initiate. Oh, so here this power source is off. Then you switch on, so you apply voltage. And by the way, this is more like a DC power source, so basically like the battery. So apply voltage. So I don't even know what you mean by connect. I mean, if you usually connect to a battery, it just like works right away. But yeah, so apply voltage. Right, observe, I guess. So graduated burette, and this is an inverted burette in a beaker. What? Why? Burette in a beaker. Okay. It's not in DI water. It's more like, okay, place electrodes in inverted burettes. Since there are like two electrodes, so inverted burettes, and place these. And fill these. So I remember the experiment, and so fill. Okay, place these in your water. So in DI water filled stuff. So your beaker. There's another step. So you have to create vacuum, right? So pull out air from burettes, so from inverted, using, I don't even know what that thing is called. It has like one mouth, and you can create vacuum with it pretty much. So I guess suck is a better word over here. I mean, it's all like filled with innuendos here and there in any case, so nothing is a better word, but I guess. So then you apply voltage to start electrolysis. Then hydrogen gas evolves at the cathode while oxygen. So we already know that the chemical reactions, bubbles should form. Repeat the procedure with tap water. So here it's not just DI water in X water, X in DI tap and NaCl. So distilled water. Wait, why is it called DI? Disionized, yes. Tap water, NaCl solution, MgCl2 solution, filled beaker. Suck out air from inverted burettes. Apply voltage. Actually, I should probably break in like, so it's not buretters, that's not correct. So here it's place it after this step. That's what we did at least. Okay, suck out the air, apply voltage. Repeat the procedure with tap water. Right, preparation of NaCl and MgCl2 solution. So it's 1 molar solution of NaCl and of MgCl2. Okay, wait. Oh, so you prepare 1 molar, then you dissolve 15 to 20 milliliter of 1 molar into 150 milliliter of deionized water. I see. Make an electrolyte solution. Sure. Solution concentrations. So this is like take 1 molar solutions of NaCl and MgCl. Right, dissolve, add 15 to 20 milliliter to 150 ml of DI water. Yep. So that's your electrolyte. This observation is like stupid because it's kind of obvious at this point. Small amount of hydrogen bubbles, but amount of hydrogen will increase after the addition of electrolytes. Very cool. I'm just gonna write that in any case. Observations. Very small amount of bubbles in DI water and then large scale yeah, that's probably it. So this is this experiment. Electrolysis is done. Let's go to the next one. So it's fingerprint. This has 3 pages. Sure. I still remember this thing. It was very bizarre, but let's just get to it. So it's fingerprint using ninhydrin. Sure. So ninhydrin is used to reveal fingerprint left at a crime scene. Actually, you know what? I'm just gonna put it after this. So ninhydrin is used for fingerprint detection. Ninhydrin reacts with amino acids found in the natural oils on our skin to produce a purple product known as Ruhimann's purple. Okay, so ninhydrin reacts with amino acids in the natural oils on our skin. So this is also in sweat, by the way, the same oils. And yeah, it was funny. I mean, we were like trying to make our palms sweaty so that we can get some good fingerprints because they were just not showing up that easily, right? To make Ruhimann's purple. So this is a purple product. Some purple product. That's cool. Alright, next thing is, so the intensity of the color may also be used as a quantitative test for the quantity of amino acids present in the sample. Also used to quantify amount of amino acids in the sample by its intensity. So obviously the more amino acids, the more intense. Okay. CVD precautions either work in well ventilated area or use different. So safety precautions. So first is work in well ventilated area or use a very dilute solution. Well ventilated area, dilute solution. It's in times like these that I wish that somebody would type for me. Okay. Because ninhydrin is an irritant. And stains skin. Biologically active reagent. Okay, this is a very bad thing. So okay, cool. That's okay. Will stain skin. So basically just keep it away from your skin as much as possible. It's irritant, it stains skin, and it's also like a biologically active reagent, so who knows what kind of thing it might do. You might just get cancer from it. But yeah, so just keep it away from your hands or face or whatever. Wear chemical splash goggles, this is a general advice. Chemical resistant. We didn't actually wear aprons, but that's fine, we had some full body clothes on. So please review current material safety data sheets for additional safety handling and disposal information. I won't. Okay, but anyway, goggles, gloves, aprons. Actually, you know what, just to make it more funny, aprons, gloves. This is better. Okay, those are the safety precautions. Then the materials. So we require test tubes, blotting paper, blotting filter, and regular. Then so 2 pieces of each. Right. Nitrogen solution in alcohol, 1% or 2% or petroleum either. 1% or 2% ninhydrin solution in alcohol or petroleum either. So petroleum ether is also flammable, so you probably should keep it away from flames in any case. 25 millimolar solution of what? L-aniline, known as amino acid. Okay, it's also known as so it is a known amino acid. Okay, I think I've seen this somewhere. Oh, L is just like it's the what the chiralness of it, right? It's like shit, I've forgotten the words, but whatever. So 25 millimole of L-aniline. This is an amino acid. An amino acid. Wait, why do you need this again? Why do you need a solution when in the end you have to use your fingerprints? Never mind. A hot plate. What the hell? Why a hot plate? Oh, we did have a hot plate and we were using it to speed up the reaction pretty much. So, catalyst. It's not even a catalyst, that's a compound usually. So, heat to speed up reaction. Okay, cool. Then a petri dish. I don't know why you require that. Petri dish. We're not biologists, bro. Forceps. Yeah, we only got biceps. Only. Ink pad, water soluble. What's an ink pad? Oh, obviously an ink pad. So it's water soluble ink pad. Why? Wait, what? Well, we don't know, but sure. Gloves, protection goggles. So gag. Gloves, aprons, goggles. I like this. Let's gag people. Anyway, so the procedure, experiment 1. Ah shit, this isn't what I wanted. I wanted a list. Okay, let's go. So first we want to take a test tube. Take a test tube, then mix the methanol. Okay, wait a second. So we want to mix methanol solution. Okay, so basically nil hydrogen. Okay, nil hydrogen solution. So it's not just an alcohol, it's more or less methanol. Next 25 millimole. Oh, this is supposed to be millimolar. Sorry for that. So this is also just millimolar, isn't it? It's supposed to be 1% or 2%, but sure. Cover the test tube with aluminum foil. Right. To start the reactions, shake the test tube careful. A light blue color will appear, indicating the formation of Rieman's blue product. Shake. So okay, I get it. You have to shake because the solvents are different, right? Isn't methanol actually soluble in water, or am I dreaming? It is an alcohol, right? And alcohols are usually soluble. Whatever. So light blue color will. I mean, yeah, it is. It's methanol, very close to ethanol, which is like actual alcohol. So why not? Light blue color will appear. This is just that Man's blue product. Okay. For the completion of reaction, heat the reaction machine in hot water bath. Heat in hot water bath. Upon heating, the intensity of the blue color will increase. Right. Intensity of blue will increase. Right, that's experiment 1. That was pretty lame, I don't know. Then you got experiment 2, where you first, so this is the fingerprint stuff. I don't want this, sorry. Okay, so this is the fingerprint stuff. So make a set of fingerprints on a sheet of blotting, filter and regular papers. Right. Make fingerprints on all 3 papers. Hold the paper in glove hand, spray the paper or dip with in hydrogen solution. Right. Spray in hydrogen. Why do you have to hold it? You can use a petri dish, right? The paper to soak for a few minutes. Let it hold onto the filter paper to drain excess solution. You're spraying it. Okay, this will prevent the fingerprints from running. Okay, spray in hydrogen. Okay. Let it hold on to the filter paper to drain excess solution. Okay, dry and then pick. Air dry using fanning motion. Hold above heat source. So this is where our hot plate comes in. We didn't have a hot plate, more like a hot brick. I don't even know what that thing was. Just a big metal brick. Metal doesn't make bricks, but whatever. So hold the paper about 10 cm above the heat source to prevent scorching. Okay, cool. So wait 2-3 minutes. Okay, a set of purple prints will appear. True. Repeat the same on second set of paper sheets, but with water soluble ink pad. Then we'll compare results on two sets. Okay, cool. So it's a pale yellow solid, reacts with amino groups in amino acid and protein to produce a purple or blue product. So this is where the important stuff is. Right, so anhydrine is a pale yellow solid. Anhydrine. Actually, no, I'm just gonna write it as a property. Properties of anhydrine. Sure. So it's a pale yellow solid. Reacts with amino groups, amino acids, and proteins to produce a purple or blue product. This reaction is slow at room temperature. Heat is used to speed up the reaction. So this is our equation. You have anhydrine and you have an amino acid, which just happens to be L-aniline. Reacts like this. Heat to speed up. Okay. They really called it perspiration, huh? Like, do I look like a tree to you? That it should be perspiration, but whatever. So the chemicals in the fingerprints include sodium chloride, amino acids, glucose, lactic acid. Okay. Glucose, lactic acid, ammonia. Yeah, I don't even know if this is ammonia or ammonium chloride or something that is going to be released, but whatever, ammonia. That's probably the safest thing to do. This is what happens, like your natural chemicals. Cool. These are results. So each group of students will produce multiple fingerprints using different type of paper, resulting in okay, clearly visible and matches with the ink-based fingerprint. So these two should be the same. Oh, okay, wait. Ink-based is just that. So during our procedure, take fingerprints. Yeah. Cool. Ah, they even put references, huh? That's nice. Finally, somebody who actually has a bit of. Oh, never mind. Okay, cool. This is cool. Next. Yeah, we got a long way to go. Glow sticks. This is the last experiment that we did, so this is like really fresh in my memory. So first is the synthesis of fluorescent. I'm gonna write step 1. Fluorescent. Wait, what? 1 gram phthalic anhydride, 1.4 gram to equivalent of. Okay. So crush 1 gram phthalic anhydride. So that's 1 equivalent. Then you crush 1.4 grams resorcinol. it's two equivalents. Using mortar pestle. Then transfer the resulting powder in a magnetic stirrer bead into 100 ml beaker. So put in 100 ml beaker. With magnetic stirrer bead. Add magnetic stir bead. Then hot oil bath. As the reaction occurs, remove the beaker from the stirrer and add more concentrated sulfuric acid to dissolve the thick paste. So remove, okay, color changes after reaction. Remove from stirrer. हाँ चल तो रही है. So it carefully add concentrated sulfuric acid. Observe the color change concentration occurs. Remove the beaker from the stirrer and add more concentrated sulfuric acid. Add more. Okay, then after the paste has melted, add water to the beaker to dilute the mixture. So I shouldn't even say dilute, more like melt. And that makes sense. So first we'll add concentrated acid so that the reaction occurs really nice, and then you'll add water to it. That's a step 1. So it's 3CPO. Sure. I kind of forgotten the full form. Okay, trichlorophenol, and you add to that. So let's just let's call it TCPO. That's it. Well, whatever. So once again, more instructions. 10 milliliter of round bottom flask must stir with a magnetic bead inside. Okay. 10 ml round bottom flask. On stirrer. With magnetic bead. Then 500 mg moleculant of 2. Okay. Cover with septum and purge with nitrogen gas. Okay. Right. Then dissolve the trichlorophenol in dry toluene. Using a metallic needle. So this is going to be like a liquid, by the way. Metallic needle. Right, add 0.35 ml of triethylamine and stir for 5 minutes. Add 0.1 ml that is oxalyl chloride. I don't know what that thing is. Chloride. I think it's oxalic chloride. I don't know. Oxalyl chloride. Halide? I don't know. To the solution while in an ice bath. So, ice bath. Alright, so you should probably write some more stuff. So stir, then you put in ice bath. Okay. Now, this is quite a bit that you have to do, isn't that right? Remove the flask from the stirrer, vacuum filter the solution, and wash the solid with methanol. The product TCPO will be a white powder. Vacuum filter the solution. Wash the solid with methanol. Sure. Amazing. So the fluorescent solution creation. Alright, so dissolve the fluorescein in NaOH solution to produce a it's just fluorescein dissolved in NaOH solution. And what else? Green fluorescent color. So fluorescent color is not a thing, more like the color is green but the solution is fluorescent, as in it emits like the captured light or whatever goes on it, it stores it and then it emits it. Then you also have this thing, cheminescent solution, which is you prepare a solution of sodium acetate. So yeah, sodium acetate plus diphenyl anthracene in diphenyl phthalate. What the? Plus diphenyl anthracene (1:1 ratio) in diethyl phthalate. This is just really weird. Small amount of TCPO2 chemiluminescent solution. So the stuff with water is usually up and the stuff with oil is down. Yeah. So the fluorescent solution is actually having NaOH, so it's going to be less dense, right? So fluorescent layer at top, since less dense, right? So I don't know what you're talking about, what sort of effect, but this is what we did. I am just gonna write it as well. So glow stick effect in dark room. Cool, that's another one. Another one bites the dust. Next we wanna go for, oh, so this is actually just another one, right? Yes, it's the same thing. So there's nothing different about it. Oh, okay, so they have added the, right. So sodium acetate, how much do you want to put? Sodium acetate, 25 mg. This is also 25 mg. Two milliliter. Hydrogen peroxide. So this is our catalyst, by the way. Nothing much has changed. Yeah, pretty much the same as before. Very cool. Then we're gonna go to methyl degradation, methyl blue degradation, sorry. This also has 3 pages. What the hell? Use light to degrade organic dye molecules, which are commonly used in dye industries. They are often present in the. Wait, shit. Is there something which I probably should? No, I don't think so. Today's November 20. I don't think there's anything that I have to do today. This is fine. Let's keep going. Okay, so we'll use light to degrade organic dye molecules, which are commonly used in dye industries. They are often present in industrial wastewater. Light to degrade. Okay, cool. We'll use regular LED torches and a photocatalyst to remove or degrade them. Okay. Often present in industrial. Oh, so this is often present in industrial wastewater. It's methylene. Iron oxide nanoparticles. nanoparticle sun. Sorry, just had to. Like, I'm sure you would have done the same. So the basic principle is the photocatalyst it absorbs light and produces holes and electrons which help in degrading the dyes. The nanoparticle may also absorb some dyes due to electrostatic interactions. Lengthy reaction. Just okay, so you get a photon to Fe3O4. It creates Fe3O4 with an electron absorbed. Wait, what? E minus. What is this? Cb. Okay, what the hell? H plus maybe the Mb plus. Something weird is happening. This is very weird. The photocatalyst absorbs light and produces holes and electrons. Oh, okay, it's a hole. This is a hole because this is an uncharged thing. This is just the light. So it's Fe3O4 plus light. Okay, so the reaction. So one is you just got Fe3O4 plus light or plus a photon. That gives, so of course Fe3O4 plus, so you got an electron plus hole plus, right? So this is basically like electrons and holes in the lattice. Okay, that's amazing. Then Mb, so methyl blue plus hole I don't know what is BB though. So that gives oxidation of Mb. Okay. So Mb is just methyl blue, methylene blue, sorry. Then water plus the whole, that gives OH plus H plus. Okay. So oxidation happens. So you actually have a plus charge somewhere. Amazing. And then okay, Mb plus OH gives CO2 plus H2O. So basically what you're saying is you're just gonna have Mb plus, right? Yeah. I still don't know what kind of positive charge you have, so I'm gonna write just plus. This is an unbalanced reaction, by the way. We have no idea what kind of charge this actually has. It's not OH. The OH is very unstable. You're not gonna have that. So it's CO2 plus H2O. Is it OH or what? No, it's something. Okay, it's not methyl blue plus. It's rather, so it's OH dot. So it's a free radical. So this one is like not important, is it? So there's actually the charge is just given like that, right? Okay. It's now H2O. Just the whole that gives us OH free radical plus H plus. Sure, that should make sense. Cool. And then finally, yeah, this is okay. H2O just goes to hell. We don't care. Plus something, so plus stuff. It degrades, that is. Wait, no, it doesn't actually, right? This is going to be a clean sort of degradation with just CO2 and H2O. This is all unbalanced, sure, but it's fine. It's the procedure. It's going to be some long time. Okay, I'm having a bit of a headache, so scrap that. Let's just complete this and then I'll take a rest. So prepare 3 vials with the following details. So vial 1, it's 5 ml. Vial 1, methylene blue, or I can say MB, stock solution, plus 5 mg of Fe3O4. Vial 2, 5 ml methylene blue, mg Okay, just as I remember, put vial 1 near the magnetic post or bar to remove the nanoparticles, and then take 2 ml of the sample and measure absorbance spectrum. Okay. In every 10 minutes. 1, you will put vial 1 near the magnetic post or bar. Okay. Put vial 1 near magnet to remove the nanoparticles. Remove Fe3O4. Take 2 ml of the sample. And measure absorbance spectrum. Put sample back. Okay, cool. Do same. Okay. Okay, cool. This is fine. Then determination of concentration from absorbance. Okay, cool. Whatever. This is the procedure, isn't it? Yeah, actually. Cool. Next, what we want is determination of concentration from absorbance. Sorry. Here is the path length. Okay, cool. So in our case, since alright, that's fine. So the molar excitation coefficient, probability of molecules, C concentration is the path length of the molecule. So another constant absorption is proportional to concentration. Shock relation with known concentrations. Okay, with the following 5 test tubes. So this was just the calibration. Okay, so wait a second. Yeah, first you have to do the calibration and then you have to sure calibration before procedure. Okay, that's amazing. Oh, okay, so it's part per million, right? So it's 30 ppm. Yeah, just 30 by 3, that's 10. Why is this happening? 30 by 4, which is like what, 27, 7 point. Okay, and then you got 2, so it's just 7.5. This is by 5, so it's just 6. Sure. So you do this thing, then okay, so you got a bunch of test tubes. Then take 2 milliliter from each of the test tube. Measure the absorption spectra. Okay, so this is just the absorption absorbance versus concentration graph, right? Sorry, versus wavelength graph. Right, take the peak. So it's like around 664 nanometer. Calculate E. Okay. Plot concentration, whatever. C versus graph. Right. Alright. Then calculate the right. So since L equal to 1, so calculate the concentrations of LD in while 1, while 2 and while 3 at different time. So this is in the procedure, right? So the vials, then you got a calibration, then finally you have the procedure. Okay. At different time. So measure E for each vial at different times. What's the interval though? Yeah, 10 minutes. Then plot the natural log of C0 versus C versus T for vials 1, 2 and 3. Calculate the slope from each graph, and C0 is the concentration of MD at equal to 0 time. Comment on the kinetics of the reaction. Okay. Right, then we convert to concentration first. Calculate C from these So your report should include the following data: all absorption spectra. Okay, absorption spectra values from test tubes quantified particle concentration epsilon values of MB log C naught by C for T vials and T. These three plots should be reported in one single figure. Yeah, whatever. This is fine. So yeah, that's methane glue degradation. Now we have a final thing. Nylon. Ah, thank God, it's a smaller one. Okay, synthesis. It's a nylon synthesis. So the two most important kinds of nylons are nylon 66 and nylon 6. So two most important nylons are nylon 6 and nylon 66. Okay. This is just history at this point. Is a polyamide. So it's textile and plastic. I'm just going to name something. Hexamethylene diamine. Hexamethylene diamine. HMDN. Okay, so add HMDA to 0.5 molar NaOH. Let's add this thing to water. Okay, I think this is fine. Next lap done. I'll have to, kind of memorize this stuff. So I'll see you guys in the next video.